My name is Hannah Augusta, and here I'll be presenting the motion of a falling object lab for Physics 1. So the purpose of this experiment is to observe the motion of an object that is dropped from rest at a certain height and compare it to that of two slightly different computational models, with one including drag and the other including gravity and drag. This graph shows a preview of the outcome of this experiment, where the motion of the object I dropped and the computational model of drag and gravity were very similar. The first fundamental principle that is vital for this experiment is Newton's second law, which states that the net force is equal to the derivative of momentum over time, which is another way of saying is equal to mass times acceleration. This is related to this experiment because the object that is being dropped will be constantly under the force of gravity and drag, which affect acceleration. The net force is also equal to the overall sum of all forces acting on the system, which in this case is just gravity and drag. Another important thing that I already mentioned is the gravitational force, which is equal to the negative of mass times gravity times j hat, where j hat is a unit vector equal to 0, 1, 0 in this scenario. Drag is equal to negative b times the magnitude of v squared times v hat. Knowing all of these will be a big help in creating the computation model. Other relevant formulas include the velocity update formula, the average velocity formula, and the position update formula, which is just a rearranged version of the average velocity formula. So in this experiment, my system was a ball of paper and surroundings were the earth and air. The initial position of the ball was 1.848 meters, the velocity was 0 meters per second, and the time was 0 seconds. As you can see in this video, I dropped the ball of paper from rest along a tape measure, which is used to calibrate the tracker. There are 30 frames recorded per second for the tracker, and a point was plotted for every one over the span of 0.733 seconds, with the final position being 0 meters. The initial position, time, and velocity for the computational model with only gravity created in GlowScript were set to be the position, time, and velocity seen in the experiment, which were 1.848 meters, 0 seconds, and 0 meters per second, respectively. The calculation loop spanned 0.733 seconds and the net force equal to the negative of the mass of the ball times gravity times j hat. The ball's velocity was set equal to itself plus acceleration times delta t for every time it went through the loop. The position of the ball was set during every loop to itself plus velocity times delta t, and its mass is 0.01 kilograms. Lastly, b, the drag coefficient, was set to 0 for this model. The code of the computational model with drag is similar to the one with only gravity, but there are some changes that I made. For this model, I set b equal to 0.0071, and I found this by experimenting with the value until the final position of the model was almost equal to that of the observed. The net force was calculated by adding the force of gravity and drag, which was done using the formulas shown previously. Here, you can see the graph that compares the positions of the tracker with the computational models. The lines for the model with drag and the tracker are very similar, which makes sense because in the real world, drag is present and will affect how fast an object falls. The computational model without drag falls faster and reaches a position below that of the other lines. There is some error in the observed data because it is not equal to the computational model with drag, but the difference is so small it can be considered negligible. Potential errors in this lab include human and computational. For human, there's a chance that I dropped the paper ball with an applied force, causing it to fall with initial velocity instead of from rest. For computational, I might have inputted the wrong data points into the tracker or incorrectly created the computational models while coding in GlowScript. The computational model that includes drag is shown to reach a terminal velocity, as seen in its graph. Over time, velocity becomes constant, which means that acceleration and net force are 0. This happens because the force of drag and gravity have become equal to each other, resulting in them canceling out. If the object was initially thrown downward, it would still have the same terminal velocity as seen with these two graphs. The only difference is that terminal velocity is reached slightly quicker when there's initial velocity compared to when the object is dropped from rest. So, in this lab, I observed the motion of a falling object and compared it to two computational models and also utilized Newton's second law, gravitational force and drag force throughout the experiment. The motion of the experiment and the computational model with drag are very similar, because air resistance is present in the real world. Thank you.